Welcome to EPG Pathsala Architecture lecture series for MArch students. And in this module, we are going to see the solar PV systems part 3. And here we are going to see the PV system design and various applications of solar PV systems. And a solar PV system design can be done in 4 steps. Number 1, it is a load estimation. Number 2, estimation of number of PV panels. Number 3, estimation of battery bank. Number 4, cost estimation of the system. Before we install the solar PV system at home or commercial buildings or for the power plant, and we have to follow all these steps while we doing the solar PV system design. And assumptions for design for actual real data to be used. And inverter and battery efficiencies are 90%. So, the combined efficiency, that is inverter efficiency into battery efficiency, and inverter efficiency is 90% and battery efficiency is also 90%, 0.9 into 0.9, that is 0.81, that is 81%. Depth of discharge, it is about 80%. And here the design of solar PV system for 2 CFL lights, 2 fans for a particular home application. Various data had given below. Battery voltage used for operation, it is about 12 volts, and battery capacity 120 ampere hours. Sunlight available in a day 8 hours per day, equivalent of peak radiation. Operation of lights and fans 6 hours per day on PV panels. PV panel power rating is about 40 wattages. And so, these are the datas necessary before we do the solar PV system design. What kind of battery we are going to use, and how long the sunlight is available in a day, and how many hours we are going to operate the lights and fans at home, and what kind of PV panel we are going to choose. And so, these things have to be studied before we do the solar PV design. A factor called operating factor is used to estimate the actual output from a PV panel. The operating factor can vary from 0.6 and 0.9 in normal operating conditions depending on temperature, dust on module, etc. Actually, the operating factor will be in the order of say from 0.6 to 0.9 because of high temperature. When the temperature is very high, when the heat is high, then the efficiency may come down. Same way, when because of the dust particles upon the glass, and it will bring down the efficiency. The operating factor has to be used while we do the design. Here we have taken 0.75 as the operating factor, and the actual output power of a 40 wattage PV panel. Here we have chosen a 40 wattage PV panel, and if it is 0.75 is the operating factor, 0.75 into 40, then we get only 30 wattage. And steps to design a solar PV system. Number 1, find out total energy requirement of the system, that is the total load. And first of all, we have to identify what is the load for a particular home or commercial building, and how many lights we are going to operate, how many fans we are going to operate, what are the gadgets we are going to operate, and everything has to be calculated, and the total requirement of the load has to be assessed. Here the total connecting load to PV panel system, number of units into rating of equipment. Here we consider 2 CFL lamp and 2 fans, and the CFL lamp wattage is 18 and fan wattage is about 60, and 2 into 18 plus 2 into 60, that is about 156 wattage we need that is the total connecting load to the PV system, and total watt hours rating, that is total connected load, it is 156, but how long we are going to operate, that is operating hours, and 6 hours we are going to operate, then and the load, it is in wattage and it is in hour, then after multiplication we get 936 watt hour, and this is the energy requirement to operate the fans and lights at home. Step number 2, find out the number of PV panels required. Actual power output of a PV panel, that is peak power rating, we have chosen it is a 40 wattage panel, and the panel will have operating factor of 0.75, and after multiplication we get only 30 wattage output. Total power used at the end use is less due to lower combined efficiency, and after that we have to incorporate the combined efficiency also. Actual power output of a panel into combined efficiency, that is 30 into 0.81, that is 24.3 watts and 24.3 wattage, and this is the total the power required. And energy produced by one 40 watt panel in a day, actual power output into 8 hours per day. So, in one day we can have sunlight approximately about 8 hours. So, 24.3 wattage we can get it, and for 8 hours we get about 194.4 watt hour. So, number of solar panels required to satisfy given estimated daily load from the step 1. So, we have calculated, that is 936 watt hour, that is the energy requirement, and here from 40 wattage panel we can get energy of 194.4 watt hour, and when we divide this we get about 4.81, roughly it is about 5 panels we need to have to operate 2 lights and 2 fans at home. And step number 3, find out the battery requirement, and we have to have the backup when the power is gone or during the night time. Definitely we need to have the battery to support the lights and fans. Total ampere hour required, total charge to be stored, that is the battery size should be higher than the actual useful energy due to less combined efficiency of the system. So, total ampere hour rating divided by battery efficiency into depth of discharge into battery voltage, and 936, that is the total ampere hour rating, divided by battery efficiency is 90%, depth of discharge is about 80%, and battery voltage about 12. When we multiply everything we get 108.33. Number of batteries required, that is equal to total ampere hour rating, that is 108.33 divided by battery rating under use. So, that is the standard battery rating is about 120, and when we divide this we get 0.9, roughly we need to have 1 battery for the storage, and to have 2 lights and 2 fans, and we need to have 1 battery for the storage of the electricity. And then we need to have the inverter. So, the inverter converts from DC to AC. The solar PV panel gives DC as the output, and we cannot use it at home because we have home appliances with AC. So, the DC has to be converted into AC, for which we need to have the inverter. So, inverter we have to choose here. So, inverter rating it is watts or VA. Total connected load to PV panel system, already we have seen that is about 156 watts, that is 156 VA. An inverter are available with rating of 100, 200, 500 VA, etc. And since it is 156, it is above 100 and below 200. So, and we can choose the required inverter as 200 watts or 200 VA, and this is the inverter selection. And for this solar PV system, we need to have 1 battery for the storage. We need to have 1 inverter which is about 200 VA capacity. And so, this is a panel we have chosen 40 wattage panel, and battery we have decided one battery and we have decided the inverter, that is 200 watts VA inverter, and we have two CFL lamp and two fans for operation. And what would be the cost of for the entire unit, that is for the above case study, the cost estimation of the PV system is done here. The cost of array, that is number of PV panel. So, we need to have 5 panels and into cost per module, and 5 panels, and that 2000, that is 2000 is 40 wattage panel, which is about 50 rupees, and then 40 into 50, it is about 2000 rupees. And so, when we multiply with 5, we need to have 10,000 rupees, that is the cost of PV array, and the PV array will have 5 PV modules, and each will have costing about 2000 rupees, and overall it is about 10,000 rupees. Cost of battery, number of batteries, that is 1. So, one battery cost, it is approximately 7,500, and totally it is about 7,500, that is the battery cost. Cost of the inverter, so one inverter we need to have, that is about roughly it is about 5,000 rupees. So, it is 5,000 inverter cost. So, total cost of the system, PV array cost about 10,000, and the cost of the battery, it is about 7,500, cost of the inverter, which is about 5,000 rupees, total it is about 22,500, and additional cost of wiring may be taken as 5% of total system cost. So, that is I mean system design and cost estimation of the PV system. This is about the PV system configuration, and this is direct conversion system, and this is the solar PV panel, and this is the DC motor, and so the panel will give a DC supply. DC motor can be operated, and the pump can be operated from the DC motor. So, here we need not have any inverter, that is direct conversion from solar PV get a DC, and we operate the motor and the pump directly. And this is about the storage system and the solar PV panel, and we need to have the charge controller to charge the battery. It will and it will avoid the overcharging, and it will take control of the battery. So, we need to have the battery, and of course, we need to have the inverter, because the DC has to be converted into AC, and then we can give the AC load for our gadgets. This is about the battery storage system, and this is about the environmental aspects. And though solar systems are so clean, and it gives only the green energy, but then it has some exhaustion of raw material and CO2 emission during the fabrication process. Of course, it uses only the solar energy. It does not matter, it will not give any pollution, but then when we make the solar PV panel, when we make the battery, when we make the inverter, and at the time of fabrication, there will be some release of CO2 and acidification and disposal problems of hazardous semiconductor material. Solar PV array, it is full of semiconductor materials, and there will be some disposal problems. In spite of all these environmental concerns, solar photovoltaic is one of the cleanest form of energy resources. Applications of solar photovoltaic system and water pumping. PV powered pumping systems are excellent, and it is very simple in design, very reliable, lifetime will be about 20 years. In the water pumping and solar water pumping, we need not have any inverter. From solar PV array, we can have a DC motor and the pump, and it can be utilized for the agricultural purposes, for the irrigation, and so we need not have any inverter here. And water pumping, solar water pumping is wonderful application for the agricultural sector. Then the commercial, for the commercial building, commercial lighting, PV powered lighting systems are reliable and low cost alternative. And so the lighting, definitely the lighting end use could be met by solar PV system. It is highly reliable, and of course, we need to have the battery storage for the continuous operation. And consumer electronics, solar powered watches, calculators and cameras, and on all everyday applications for PV technologies, and all these small gadgets like watches and calculators and cameras, and which can be operated by solar PV power. And telecommunications, residential tower, a residence located more than a mile from the electric grid can install a PV system more expensively than extending the electric grid. So, for the remote areas, for the hilly stations, instead of bringing the grid all the way, and we can have the decentralized solar PV system, and for the various applications. Over 500,000 homes worldwide use PV power as their only source of electricity. And this is about solar energy jobs, and this is estimated in the future it is going to create lot of employment opportunities. And in the country, and because of the solar mission, and lot of solar PV power plants are coming up in the country, and automatically it will create lot of employment opportunities. In the year 2010, and 93.5K employees were working. So, it kept on increasing, and in 2015, and about 209 into 1000 people are getting employment in solar based industries. So, the employment opportunities are, and it kept on increasing, and because of the solar industry. And these are some of the advanced systems, and that is about solar PVT collector here. And when we have solar flat plate collector, it occupies some area, and apart from that, when we have solar photovoltaic system for lighting application, for fan application, again, and it will occupy the area. And when we couple solar PV and thermal, and definitely the area can be reduced. These are all some advanced research is being conducted, and instead of having a separate solar flat plate collector for water heating, instead of having solar PV system separately for the electricity, we can have combination of these systems as one system, so that area can be reduced, and more than 60% additional area is required to provide the same thermal and electrical yield using individual systems. So, when we have for thermal application and electricity application separate systems, we need to have extra area about 60%. A PVT technology, and is a combination of photovoltaic components and solar thermal components, which produce both electricity and heat from one integrated component of system. So, instead of having two separate systems, we can have only one system, but we can have electricity as well as hot water. And this is the top portion of the solar PVT system, and this is it's a solar PV panel. See, and this solar PV panel will give the electricity, and the sun rays strike the PV panel, and this is a semiconductor device, and electricity is produced. At the bottom of the panel, we have the water tubes, and through the water tubes the water is flowing, and the water gets heated up, and it can be utilized for the bathing purpose. And here underneath the PV panel, and since the water is flowing, the PV panel gets cooled, and by which the efficiency is increased. Actually, the solar PV panel accepts radiation. The solar intensity, high radiation is necessary, but then and the heat is against to the panel. When the temperature is more, the system efficiency will come down, and that is why the water is going underneath the solar PV panel, and by which the system efficiency could be improved. Ultimately, we can have hot water as well as electricity generation in one system, that is solar PVT system. And a PVT solar energy system is a combination of photovoltaic components and solar thermal components, and it is integrated together. And this is about the electrical efficiency and thermal efficiency. And here we see the electricity in this is efficiency in percentage, and this is here we see from morning 10 o'clock to evening 3 o'clock, and the readings are taken. And this is about electrical efficiency, this is about the thermal efficiency. And when we look at this graph and PVT system without glassing, and when flow rate is 0.1 kg per second, and it gives better performance. The electrical efficiency is highest when without glazing and 0.1 kg per second mass flow rate. In the same way, when we look at the thermal efficiency part, and here it gives maximum efficiency, that is PVT system with glazing and 0.1 kg per second mass flow rate. And for thermal system it needs glazing. For electricity generation it does not need glazing. So, and here in the PVT system with glazing and without glazing, with the different mass flow rates, and the experiments were conducted, and it gave very good output, and both thermal as well as electrical applications. And this is about another research work, and this is about concentrating photovoltaic thermal collector. Again this is PVT system, and here you see here these are the collectors, solar PV collectors, and it is like a parabolic trough collector, and this is the absorber tube. In this absorber line, and the solar PV cell is fixed throughout absorber line, and solar photovoltaic cells are fixed here, and this is like a solar parabolic trough collector. So, the sun rays will strike the collector, and it will come and gets focused upon the absorber, and because of high radiation, because of the high intensity, and it gives better electricity production. At the same time, and the heat is also increased. When the sun rays are focused and the solar intensity is increased, as well as the heat is also increased. So, the heat will destroy the solar cell. That is why the water is admitted and underneath the panel, which will take away the heat, and when it comes out with as hot water. So, here in this system we can have hot water as well as electricity generation. Again this is concentrating solar photovoltaic system, and both applications are possible in one single system. And this is the spec of concentrating PVT system. About PV cell area, which is about 475 centimeter square, and collector aperture area, which is about 6.6 meter square, and area occupied by each collector it is about 2.2 meter square, and number of hybrid PVT receiver is 1, number of purely thermal receiver it is about 2, optical efficiency of the collector is about 99%, number of PV cells here we used about 25 cells, and concentration ratio for the system it is about 37 times the sun's effect is increased here, that is the concentration ratio. Reflectivity is about 93.5%, and tracking system also is adopted here, that is about single axis manual tracking system. And this is about the hybrid system, solar photovoltaic hybrid system, and maybe only the daytime we get the solar light, night time we cannot get it, and that is why here with the solar PV panel and the wind turbine, that the small wind turbine and small capacity wind turbine is also adopted here nearby solar PV panel. So, it is integrated together, and here one more generator. So, daytime and solar PV can generate, wind also can generate when the wind velocity is good, and night time PV panel cannot generate electricity. Of course, wind can also generate, but sometime there will not be proper wind. So, that time generator can feed electricity. So, here the wind turbine, PV module and generator all integrated together, and here we have the batteries for the storage, and here this is all the home appliances could be met by PV hybrid system. This is about solar street lighting, and here this is about the solar PV panel, and this is the battery for the storage, and this is the lamp, and that is about solar street lighting. Very small tiny components, solar PV panel and lamp and battery,
and so this could be installed on the streets where there is no electricity, where there is no grid connection, and definitely it is very good application for the lighting. And this is about the solar water pumping. So this is the PV array, and this is polycrystalline solar panels or multi-crystalline solar panels, and the two panels are set up here. And here the DC motor is operated directly without conversion of DC into AC, and DC pump the pump is also operated here. So and with the minimum number of components without any storage, directly and electricity could be generated, it can be utilized to pump the water for the irrigation purpose.
And this is about the solar photovoltaic power plant. So, here you see and a very mega size power plant, lot of PV arrays. This is approximately about 1 megawatt power plant, solar PV power plant. Of course, partially there is some backup storage batteries adopted here. And for the traffic lighting, so and need not take power from the grid. So, here just we can have some solar PV panel and it can generate electricity. Of course, we can have some battery, and so it does not consume much electricity. So, in traffic systems, traffic signals, and can be operated with the solar PV system. And in railway stations, and here and we can have the solar PV panel upon the roof of the shed, and here is a station, there is the roof here, and upon that solar PV panels are fixed and it generates electricity. Maybe it is useful to operate the signals and even for other end uses. And this is of the space applications, and it is very big solar PV panels, and when it is flying up and up and in the vacuum, definitely the solar radiation will be very good, and there will be completely direct radiation, and the intensity will be very good. Of course, there will not be heat also. It gives better efficiency, and all the controls can be operated with the solar PV power and Mars rover. And here there is architectural integration of PV modules on exterior walls. So, in the buildings, all the exterior walls, upon that we can fix solar PV panels, and it does not occupy extra area. It gives aesthetic view also, and it generates electricity, and it could be used for all lighting and fans inside the building. And this is the home, and upon that solar PV panels are fixed, and the electricity is generated, and all home appliances can be operated with the electricity produced from the solar PV panel. This is about the recreational use, sailing of boat, and here this is for the recreation, and people used to sail the boats in the sea, and during the night time, if they want to halt, or if they want to use any gadgets, maybe for charging the mobile or watching TV, etc. And so, at the stationary time, and they need not put the diesel engine, and it consumes a lot of energy. Instead, at the time of stationary, maybe at the rest time or night time, and we can have the solar PV panel and battery also for the storage, and all the gadgets can be utilized with the solar power instead of operating the big diesel engine to get the minimum power. In this module, we have seen about solar PV design and costing of solar PV system, and we have seen various applications of solar PV systems. Of course, we have seen some advanced research also in the area of solar thermal and solar photovoltaic system, and solar thermal and solar photovoltaic is combined here PVT systems, and it occupies less space, and in one system we can get electricity as well as the hot water. And when we concentrate solar radiation, the intensity is increased, by which electricity can be produced much at the same time, and when we cool the solar PV panel through the water, again we get the hot water. And so these are some of the research works carried out. And further, in the solar PV applications and solar thermal as well as solar PV, definitely there are lot of avenues to improve the efficiency, as well as there are lot of avenues to bring down the cost, and there are lot of avenues to reduce the occupational area. So, these three areas have to be concentrated again and again. We have to bring down the system cost, we have to increase the system efficiency, we have to make it very compact, and definitely in the future, and solar systems are going to play a vital role to meet the thermal demand as well as electricity demand all over the world. Thank you.